All right, today we are getting into 5-1, which is on perpendicular bisectors as well as angle bisectors. So we're going to be looking at some problems that really are just some algebra problems, really just solving equations. So that might come as a little bit of a break from the pretty intense geometry proofs that we had done last chapter. So it was a lot of proofs, which is totally a different type of math. So you'll see with these problems, we're really just solving equations. So it might feel like a little bit of a break for you with the new content and kind of going back to some solving equations. But our two new theorems are up here. And that's the perpendicular bisector theorem and then the converse of the perpendicular bisector theorem. And basically, we're just going to use these theorems to solve some triangle problems with variables. So the first thing I'm going to do is just talk with you about these theorems, and then we'll solve some problems. So at the top here, the first one is the perpendicular bisector theorem. So let's read this. And even though it sounds like a lot, we're familiar with all of these words. We've heard all of them before. We do know what perpendicular means, and we do know what a bisector is. So these are words that we've seen before. We're just putting them together and applying them to a triangle. So it says, if a point lies on the perpendicular bisector of a segment, so let's talk about what that means. Perpendicular, meaning it just cuts through and forms a right angle. And then bisector, meaning it cuts it in half. So we got a half here and a half here, and it forms a right angle. So if that's the case, then it is equidistant from the end points of the segment. So equidistant means equal distance. So that means it's the same length from the end points of the segment. So basically what that is saying in so many words is that these two side lengths right here are congruent, okay? Which we used to prove that, with a whole long proof. And this perpendicular bisector theorem is telling us that if CD is perpendicular to AB, so CD right here is perpendicular to AB, this bottom one, and AD, so right here, AD is congruent to DB, so all of that is marked here, then that means that AC is congruent to CB. So let's write that. AC is congruent to CB. So that's what the perpendicular bisector theorem is telling us. That if this is a bisector, if it's perpendicular, and then these are congruent, then that means that these ones are also congruent. Okay? And then the converse of that, of course, let's do that backwards. So if AC is congruent to CB, so if we already knew that these two were congruent to each other, then that must mean the opposite. Then that must mean that CD is perpendicular to AB. And it also must mean that AD is congruent to DB. All right, so just the opposite of that. So if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. All right, so all of that is a lot, and we're going to use it to solve these examples here, which is just finding x. So if we know that two sides are congruent to each other and we don't have x, we can use a simple algebraic equation to solve these. So let's start with number 1 here. I'll show you an example. So this image right here, you have a triangle. It's a perpendicular bisector right here, cutting this side length right here in half. So you have these two equal sides. So then our knowledge here is to know, well, that if these are equal, then that means that these are equal. If I have a perpendicular bisector and it's cutting this in half, then these two are equal to each other. So how could we solve for x in this case? We would simply set those two equal to each other and solve. So I am going to put here 7x plus 24 equals 13x minus 48. And then I'm just going to solve that equation. So this is really just some algebra that we've seen a million times at this point, and that we're just going to go ahead and solve. So my first step here, I am going to go ahead and subtract 7x from both sides. That cancels. That's going to give me 6x minus 48. And then I will add 48 to both sides. All right, and I will get 72 equals 6x. And so that is going to leave me with x equals 12. And that's my answer. So that was really purely algebra, just setting those two equal. The reason that I knew I could set those equal to each other was because of the perpendicular bisector theorem. All right, so let's take a look at number 2 as well. So now, if you notice, we're looking at the converse. So instead of having, this perpendicular bisector noted and these two equal to each other, we just have that these two side lengths here are equal to each other. So then we would infer that these two are also equal to each other. So I'm going to set those two equal to each other and solve. And I would encourage you to, try this problem out yourself. Just get some practice solving equations. If you haven't done it in a little while, just to refresh your memory a little bit and make sure you still know all of those steps right there. And I'm getting x equals 2. Okay, so 1 and 2, we just had to solve for x. Now, if we look at 3 through 6, we're actually going to be finding a side length. So, for example, number 3 says to find RS. So I actually want to know the exact value of this side length here. So what am I going to do first to solve for x? Yes, I'm going to set these two equal to each other. So I'm going to do 7x minus 22 equals 4x plus 5. And then I'm going to go ahead and solve that. Subtract 4x from both sides. I get 3x minus 22 equals 5. Then I will add 22 to both sides. Three x equals 27. So x equals 9. So that's half my answer. Now I need to go back. They asked for this actual side length right here. They want to know what this is. So I have to plug that back in over here in order to figure out actually what that is. So I'm going to do 4 times 9. Put it right here. Let me just write that out just so you can see. So I'm going to be putting 9 in right there. So that's going to be 4 times 9 plus 5. So that is going to be 36 plus 5, which is 41. All right. So again, this is just some algebra problems. Maybe this is your preference over geometry, maybe it's not, or maybe neither. But this is going to be the gist of these problems. So, of course, I'm going to have you try number 4 on your own, and we'll meet back up and see what you got. All right, so you can see number 4 here. What you should have gotten for your final answer was 19. We solve for x, we set these two equal to each other, get x equals 4, and then when we plug 4 back into EG, which is this part right here, 2x plus 11, we get 19 as our final answer. So I am going to show you number 5 because it's slightly different. And then I'll have you try number 6. So the reason number 5 is just slightly different, let's take a look at it, is it says find AB. And if you notice, AB is the entire segment as opposed to just half of it. So just going to be slightly more work for us. So we're going to do here first is the same thing that we've always done. We're going to set these two equal to each other. So I'm going to have 5x minus 11 equals 3x plus 17. I'm going to go ahead and solve that. So I am going to subtract 3x from both sides. So I'm going to have 2x minus 11 equals 17. Going to add 11 to both sides. Let me zoom in here. So I'm going to get 2x equals 28. And then I'm going to divide by 2. So x is 14. So that's just half of it. Now that I know that x is 14, I do need to go and plug 14 into both of these expressions here. So that's going to give me for AD, let's start with AD, which is 5x minus 11. So that's going to be 5 times 14 minus 11. So that's going to give me 70 minus 11, which is 59. So 70 minus 11, which is 59. Unfortunately, that's only what AD is. So now, since this is 59, remember that these are equal to each other, right? So what's 59? Either 59 plus 59 or 59 times 2, we can say. So AB, I'm going to write here, would be 2 times 59, which would be 118. And that would be our final answer for number 5. So just an extra step right here. They wanted to know the entire thing. So I had to multiply it by 2 to get 118. And then let's see. So number 6 is actually, looking back at it, it's going to be quite similar to 3 and 4. So I'm going to have you try number 6 on your own, and then we'll see how you did. Okay, so you can see the final answer to number 6 is right here, which is 94. So I, of course, set these two equal to each other. I solved my equation. I got x equals 20. And then I plugged that back into JK, which was 6 times 20 minus 26. That shouldn't be there. And then I get 94. That's my final answer. So more than likely, your mistakes on these problems are just going to be somewhere where you're solving the equation. A simple mistake, usually it's with integer operations, adding a number instead of subtracting it or something like that. So just important to double check your work, be careful, use a calculator to double check your operations, make sure you did them correctly and things like that. And now we're going to go ahead and move on to angle bisectors. So it's actually going to be very, very similar to perpendicular bisectors. If you go to the back here, the paper looks very similar, but now we're going to be talking about angle bisectors. So when we chop an angle in half, right? So that's what a bisector is. So let's take a look up top at our theorems right here. The angle bisector theorem, and then the converse of the angle bisector theorem. So the first one says angle bisector theorem. So if a point is on a bisector of an angle, then the point is equidistant from the sides of the angle. Okay, so here we're calling this ray. So if ray AD, so this line right here, if it bisects angle BAC, so this angle right here, so if it's cutting it in half, and AB is perpendicular to BD. So if AB right here is perpendicular to BD, this little segment right here, you can see that it's perpendicular by our right angle right there. And then AC, so the other side is perpendicular to CD, then that means that these sides right here are congruent to each other. So that means that AC is congruent. That means that I meant to point at these ones right here. So it means that these are congruent to each other. So that means that BD, sorry, not AC. That means that BD is congruent to DC. Oops, and I wrote that wrong again. Whoops, BD. My apologies. So that means that BD, this one right here, is perpendicular to DC. It means that those two are congruent to each other. BD is congruent to DC. All right, so that's the angle bisector theorem. Let's take a look at the converse of that. So now we're just going to take all of that and say it backwards. So if BD is congruent to DC, so if these two are congruent, and then AB is perpendicular to BD, AC is perpendicular to CD. Okay, so same as before. Now we're going to go backwards. We're going to go over here and say that this part, AD, ray AD, bisects angle BAC, which we know, remember from, angle bisector, we know that that means that those two angles are congruent, which is the whole purpose of that theorem as well. So I'm going to put right here in parentheses that the measure of angle BAD is congruent to the measure of angle CAD. So these two angles are congruent. So the important stuff for us is, these are congruent, these angles are congruent, and we're going to use that knowledge now to just solve some problems where we find the value of x. So we find those either missing angle values or missing side lengths. So it will be very similar to perpendicular bisectors. So if I look at number 1, this goes back to this top theorem up here. So I have an angle bisector right here. I have these perpendicular segments right here, which then means that these two, as stated in the angle bisector theorem, these two are equal to each other. So I'm going to go ahead and set them equal to each other, and then I'm going to solve for x, since they just asked to find the value of x. So I'm going to say 4x plus 30 equals 9x minus 5 and go ahead and solve that. Of course, if you would like to do that on your own, feel free. I'm just going to go ahead and do it here, and then I'll give you some others to try as well. So I'm going to subtract 4x from both sides. So 30 equals 5x minus 5. Add 5 to both sides. 35 equals 5x. And then I'll go ahead and divide by 5. So x is 7. Okay, so let's look at just the difference real quick as the images of perpendicular bisectors. So just to kind of compare what we have, we're really looking at the angles. We have an angle bisector right here, as opposed to a perpendicular bisector. So that's kind of just the difference with the images. And now, so I have this is perpendicular, and then these are congruent right here, which then means by the converse of the angle bisector theorem that these two would be congruent to each other. So I'm going to write down 5x minus 11 equals 8x minus 41. And then I will go ahead and solve that. So that's going to give me 5x, minus 5x here, minus 5x here. So that's going to give me negative 11 equals 3x minus 41. Then I will add 41. Here's a common mistake I always see right here. We have negative 11 plus 41. Just make sure you don't go ahead and say that that is like 52 or negative 52. Think of that as 41 minus 11. So you're really subtracting that 11 from 41. So you're going to get 30 equals 3x. Your most common mistakes are just integer operations, making little mistakes like that. So just be careful. And x equals 10 is what we would get for that one. All right, so number 3 is just like, number 3 from our last type of problems with perpendicular bisectors. So I'm going to go ahead and see if you can try, we'll say 3 through 6 and see how you do.